Okay, so let's talk about properties of functions. First thing we're going to do is talk about a couple of definitions, an even function versus an odd function. So let's go with the definition of an even function first. How do we identify an even function algebraically? Here's how we do it. So we are going to replace x with negative x. If you see an if, there's going to be a then, so these statements are very important. If f of negative x is actually equal to or the same as f of x, which was the original function, then. So here's what I need you to understand. The if is the requirement. The then is the result. So if this requirement is met, if when I plug in negative x, I actually end up with the original function, then f of x is an even function and symmetrical with respect to the y-axis. So, algebraically speaking, if you plug in a negative x for wherever x was, and you end up with the exact same function as the original function, then f of x is considered an even function, and graphically speaking, it's going to have symmetry with respect to the y-axis. Cool? Okay, so let's talk about an odd function. How do I know when I have an odd function? Well, we're going to start the same way. We are going to replace x with negative x. If f of negative x, when we make this replacement, if it looks like, now just pay attention a second, if it looks like I took the original function and multiplied it by a negative, or a negative 1, if you'd like to say it that way. If it looks like I took the original function and multiplied it by a negative, then, again, if is the requirement, then is the result. Then, f of x is an odd function and symmetrical with respect to, remember the WRT is my shorthand for with respect to, the origin. So algebraically speaking, if I plug in a negative x for wherever I see x, and I end up with taking the original function and multiplying by a negative 1, which means every sign changes, agreed? Then f of x is an odd function, and graphically speaking, it has symmetry with respect to the origin. Cool? Okay, so hang in there. I'm going to get some examples. Okay, so let's look at these particular examples. The directions ask us, is this an even and odd, or maybe it's a function that's neither even or odd. So let's take a look at number 1. Now, in order to determine if this is an even function or an odd function, or again, maybe it's not either one, because you know as well as I do, not all functions are going to have symmetry, right? So if we're going to determine if it's even or odd, or maybe either one, neither one, then we have to plug in what? Yeah, we have to plug in a negative x, don't we? Okay, so that means I'm going to take f of negative x, and I'm going to plug it into this first function, which means I get a negative 3 times the quantity of negative x to the power of 4 minus 5 times negative x to the power of 2. All right, so let's simplify and see what we get. So answer me this. If I take a negative number and I take it to the 4th power, what will that be? Yeah, that'll be a positive number, won't it? I may not know what x is, but I know this will be a positive number, agreed? So wouldn't it be the same as taking x to the power of 4 and the negative will just come positive? Good. And then I have minus 5. Remember, exponents come before multiplication. And I take this negative number to the second power. Yeah, it's going to be positive also, which means I'm going to get 5 to the second power. Agreed? All right, so the question is this. When I took the function and I plugged in a negative x, did I come up with the exact same as the original, or does it look like I took the original and multiplied everything by a negative 1? What does it look like to you? Yeah, it looks exactly like the original, isn't it? Wonderful. So is this an even function, or is this an odd function, or maybe it's neither one? Good, I heard you. This will be an even function. Okay, so since it's an even function, what kind of symmetry does it have? Yes, it's symmetrical with respect to, that's right, the y-axis. Right? Okay, got it? Let's take a look at number 2 here. And we are supposed to plug in, yes, we're supposed to plug in a negative x. So let's see what happens when we plug in a negative x. So f of negative x equals, we've got a cubed root, don't we? Of 5 times negative x. Agreed? Well, that's going to be the cubed root of a negative 5x, isn't it? Okay, so we've discussed this before, so let's see what you remember. If you take the cubed root of a negative number, your answer is going to be what? Yeah, your answer is going to be negative, which means the negative will come out and I'll have the cubed root of 5x. I may not know what 5x is, but I know when I take the cubed root of that negative number, I'm going to get a negative answer, aren't I? Okay, so when I took f of negative x, here's the question. Did I get the original function back? Or does it look like I took the original function and multiplied by a negative 1? Yeah, it looks like I took the original function and multiplied by negative 1, doesn't it? Which means, that's it, I heard you, this is an odd function. And what kind of symmetry does it have? Yep, that's it. Symmetrical with respect to the origin. Cool? Now, do you notice I have either a y-axis symmetry or an origin symmetry? I don't have x-axis symmetry, do I? And you're like, well, why is that not true? Why don't I have x-axis symmetry? Well, go back to one of the previous lectures where we talked about symmetry. If you're going to have x-axis symmetry, that means the y's are changing. Again, if you're going to have x-axis symmetry, your y's are changing. Even symmetry says you plug in for x. Odd function tells you plug in for x. Both of these odd and even functions mean you're plugging in for x. X-axis symmetry doesn't have plugging in for x, which is why we'll never have an x-axis symmetry when we are speaking about an even function or an odd function. Good? Okay, I have a couple more examples. Okay, so let's take a look at this third example. They're asking us if this is an even function or an odd function, or maybe it doesn't fall into either category. So how are we going to figure it out? Algebraically, we plug in a negative x for wherever we see x. Agreed? Okay, so we're going to take f of negative x. We're going to plug that negative x in place of x, which we just did. Let's simplify. Okay, so what happens when you take a negative number to an odd power? Good, you get a negative answer, which basically means I've got 9, right, times this negative x, which means this is going to be a negative 9x to the power of 3, isn't it? And I still have a minus 5, don't I? Okay, so when I plugged in the negative x, and I am going to scoot my equal to sign over just a wee bit so it's easier to see. I end up with a negative 9x to the third minus 5. So here's the question. Did I get the exact same function? No, I didn't. Does it look like I took the original function and multiplied by a -1? The whole function? No, it didn't, because only the first term switched signs. The second term is exactly the same. So the entire function did not get multiplied by a -1. So is it an even function? No, because it's not the exact same. Is it an odd function? No, because it doesn't look like both terms got multiplied by a -1. This one's neither. It's neither odd or even, which means it doesn't have any it doesn't have any y-axis or origin symmetry either. Got it? Okay, now let's take a look at this fourth one here. And again, in order to figure it out, we need to plug in a -x to determine if this would be an even function or an odd function. Or again, maybe it falls into neither category. So let's check it out. We're going to take 3 times the -x, correct, plus absolute value of -7 times -x, right? Okay. Yeah, the first term will be a -3x. The second term, yeah, it's still going to be positive, isn't it? Because this is in absolute values, and this will be a positive 7x inside absolute values, right? Okay, so here's the question. Did this come out exactly like the original? No, it didn't. Does it look like both terms switched signs? The first term certainly did. It went from a positive to a negative. But if you notice the second term, it's still a positive, isn't it? This absolute value tells me no matter what's inside here, it's going to be a positive answer. And with a positive out front, it's not changing, is it? So is this an even function? Nope. So no y-axis symmetry. Is this an odd function? Nope. So no origin symmetry. This one, again, just like the last one, this one represents neither even or odd. Cool? Okay, be careful. Both terms need to switch signs. All terms, I should say, because maybe the function has 3 terms in it. But all terms need to switch signs. Cool? Hang in there. We're moving on to some. Okay, so let's take a look at a definition called local maxima. I've already written it out, and I want to go over it a little more in depth. So we have a function f, and it says a function f has a local maximum at c. C is just some number. I don't know what the number is. It doesn't matter what the number is. So this function has a local maximum located at C if there is an open interval. You're like, what's an open interval mean? An open interval means we have parentheses, not brackets. Cool? If there's an open interval I containing C, so that for all x not equal to C in I, gratefully there's a comma there, so we're pausing. So you're like, whoa, that's a mouthful. It is a mouthful. So understand something. There's an open interval, which means we have parentheses, and we just gave it the name I. So don't get too bogged down in the name of the interval. It's just called I. But what we do know is this open interval contains this number C. Now, this part's actually quite important because it tells me something. So that for all x's not equal to C, and again, we're in the interval. So for all x's not equal to C, here's what that means. C is a number, right? It's in this interval, correct? No other x is equal to C, right? So here's what that tells me. It tells me that I is representing the domain, which means C is in the domain. So this C actually represents some x value, but we're calling it something else to make it stand out. With me? Okay, so let me go back. They're telling us a function has a local maximum at this number C which we now know is in the domain, if an open interval I, which is representing the domain, contains this number c, so that no other x value is equal to this c value in this interval. Okay? So it's unique. It's a unique x value. With f of x less than f of c. Okay, so hold on. What does f of x mean? Yeah, it's a y value, isn't it? Right? F of x is a y value. But f of c is also a y value, isn't it? Because it says function of c. So here's the thing. This is the y value at x. This is the y value at c. And it tells me all these y values are less than the y value that's at that one number c. If this is all the case, because remember, I've got an if-then statement going on. I've got if this is true, if I have this open interval that contains c, so that no other value is equal to it, and all the other y values are smaller than the y value at c, then f of c is called a local maximum of the function f, and it's located at the number c. Okay, hang in there, because if I have a local maximum, then I can have a local minimum. But the cool thing about math is if you know one definition, you pretty much know the other. So, let's reread it, but now we're going to talk about minimum. So a function that we're calling f has a local minimum at this number c, which we already know is in the domain, if there is that open interval again that we're calling I, and it contains that number c, so that all the other x's are not equal to c. All the other x's are unique away from c. In I. With f of x, now it's not less than, now it is greater than f of c. So all the y values at x must now be greater than the one y value at c. Then f of c is considered a local minimum of f located at c. So if I have a local maximum, I have a unique y value that's the largest y value for the entire graph. If I have a local minimum, then I have a unique y value that's the smallest of all the other y values. Understand, when it says unique, it means one of a kind. With me? When I say unique, or the authors of the book say unique, it's one of a kind. No duplicates. Okay? No duplicates. It must be the only one. The largest one or the smallest one. That's it. Cool? Okay, so we're going to go through some examples of these. So stay tuned for some graphing. Okay, so let's talk about some properties of these functions. Let's take a look at this graph. This graph is asking us to find the intervals on which this function is decreasing. I'm also going to ask us to find where it's increasing and where it may be considered constant. Now, when you read a graph, you always read from left to right. Why? Because you're always reading based on the x's, and you're always reading from the smallest x value to the largest x value. Okay? Okay, so give ourselves some space. I want to find increasing and where it's decreasing. And where it would be considered constant. Okay, so let's take a look at this graph. Let's first find where it's increasing. So when we start off reading from the left, we notice that the first thing it's doing is decreasing, isn't it?
Okay, so I'm not looking for decreasing, I'm looking for increasing. And I'm noticing at this particular point is where the decrease stops and the increase starts. So at this particular x value, which looks like it's at -9, is where our increase will start. So it looks like this increase starts at -9 and ends here, correct? Well, that ending looks like at -3. So I have one increasing interval that starts when x is -9 and ends when x is -3. Let's see, is there any other place where this graph is actually increasing? Yes, it looks like there's another increase starting right here, and that looks like it's at -1, and this increase ends at this point, correct? But that's where x is +1. So, looks like we have another increase starting at -1 to +1. And looks like one more increase starting at 4 for the x's and ending at 6 on the x's. Now that's a solid dot right here at the end, so that's definitely not going to infinity. That's starting at 4 and ending at 6. Now, depending upon the author of the book, they may put parentheses around these or they may put brackets. And you're like, well, why brackets? Because all of those were solid dots, so they should all be brackets, not parentheses. And I understand that. But also understand that these solid dots, this is where the graph is making a turn from an increase to a decrease, or vice versa, from a decrease to an increase. So sometimes that's considered the neutral zone, so to speak, where it's not really increasing or decreasing, a turn is happening. Now, the author of this particular book does put brackets around these because this author does consider that these solid dots should be brackets. And I am just going to put a comma in between them. There is no union symbol here. Okay, these are the three intervals where we're having an increase, and that's all that we need to know. Good? Okay, so let's look at a decrease. Now, the decrease, we already know the very first interval will start with this particular point and the decrease ends at this point, correct? But remember, we're always reading based on the x's. So this looks like it starts at -11 and ends at -9. So this decrease starts at -11 and ends at -9. Okay, let's see if there's another decrease. Looks like it starts decreasing from this point to this point, correct? Well, that looks like it's at -3 and it ends at -1. And I got another decrease. It looks like it starts at this point and ends right here. So that looks like it goes from 1 to 4. Now remember, the author of this book puts brackets around these because there are solid dots, so it doesn't consider any neutral zone, so to speak. And then last but not least, do we have any intervals where this would be a constant function? Now, some of you may not be aware of what I mean by a constant function. A constant function is like a flat line, like maybe this. This part right here would be considered constant. This part would be an increase, this part would be a decrease, but that part would be considered constant because it's a flat line. Do you see that on this particular interval where it doesn't change? No, neither do I. So let's go back a second. So what you are telling me, and I should write none here so we have that taken care of. What you are telling me is this. This particular graph starts a decrease from -11 to -9 because as soon as it hits -9, it increases until -3, and as soon as we hit -3, it decreases until -1, and as soon as we hit -1, it increases until +1, and then as soon as we hit +1, it decreases until 4, and as soon as we hit 4, it increases until 6. So we have every part of this graph covered. Good? Okay. Let's take a look at this one. They're asking us, by looking at this graph, is f increasing on the interval from 3 to 5? Now remember, 3 to 5, this interval represents what variable? Good, this represents x. So I'm going to look at the x's, and 1, 2, 3, and to 5. And they want to know if from 3 to 5, this graph is increasing. What would you say? Yeah, no, this graph is not increasing. It's what? It's decreasing from 3 to 5. So that takes care of that one. Let's look at this next one. They would like to know, is there a local maximum at x equals 4? Well, x equals 4 is here, and they want to know, is this point considered a local maximum? Now, understand something by the definition of a local maximum, right? We're looking at a particular open interval. And if we take a look, this interval we could be looking at goes from negative infinity to positive infinity, couldn't it? We could technically look at negative infinity to positive infinity. That is an open interval. And x equals 4 is a unique x. There's no duplicates. We just have 4 appearing once on the number line, don't we? Good. So, and we need to know if the y value that goes with this particular x is the largest value, largest y value out of all of the y values on this graph. And that looks like it is, correct? Okay. So, would you think that there is a local maximum at x equals 4? Yes, that's true. The answer here would be yes. Definitely there is a local maximum. Now, I could ask you a follow-up question on this. I could ask you, what is the local maximum? So, you would have to know this y value, wouldn't you? So, this is 4, comma, what is this? Looks like these are in increments of 2, and that looks like it's 16, isn't it? So, what is a local maximum? That's a y answer, so you better write y. Y equals 16. Make sense? What is a local maximum? And then where is the, pardon me, I'm rephrasing my question in my head, sorry. Where is the local max occur? And that would be at x equals 4. Where does the local max occur? It occurs at x equals 4. And what is it? Is y equals 16. Be careful of the words where and what. Cool? Okay. How are we doing? So far, so good? Loving it. All right. Let's take a look at this one. Now, this graph looks familiar. It looks like one of the first ones we did. Now, this has an interesting question because this is asking for an absolute minimum. Now, if we take a look at this graph, they're asking for negative 12 to 5. First of all, which variable is that representing? Good. This is representing x. So, from negative 12 to 5, I have a lot of dips in this graph, don't I? I have a lot of minimums in this graph, don't I? You see that? Now, they have a key word here, and the key word is absolute. And when they say absolute, they want to know which one of those minimums is the lowest minimum on this entire interval. Well, the lowest one is right here, isn't it? And I'm going to erase this so we can see it a little better. This looks like the point negative 10, comma, negative 2. So, this is your x, correct? This is your y. So, notice how this is written. Should it be A or B first off? Good, it should be A because we do have an absolute minimum. Now, f of something equals something. So, Remember when you usually write f of x, right? Equals a y answer, don't we? So in this particular case, your x was -10 and your y was -2. Remember, this is the typical way of writing the function. Does that make sense? Okay, so remember, absolute minimum means the lowest point on this entire interval. And since I had 3 what could have been considered minimums, the absolute one, the lowest one, was at the point the lowest absolute minimum occurred at, so I'm going to write a little bit differently, occurs at x equaling -10, and the local minimum is y equals -2. So other language we can use. So be aware of that other language. Okay? All right, let's keep going. Looks like we got a 4-parter here. That's okay, we can handle it. Now, mind you, with all these graphs, I could ask you oodles of questions. Notice this particular graph. They're asking me for the intercepts, the domain and the range, the intervals where it's increasing and decreasing, and where it's even, odd, or neither one. I could also ask you for local mins or local maxes, depending upon the interval. So just understand that. I could ask you oodles of questions on one graph. So always be aware of that, okay? All right, so I am going to, on this separate piece of paper, we're going to do part A, and we're looking for intercepts. Now, did it say X or Y intercepts? No, it just said intercepts, which means you've got to find them all. So I'm noticing this point and this point and this point. These are all crossing the axes, yes? So my tick marks are in increments of 1s. So this looks like what? Right here. Yep, that looks like -1, 0. What is this one? That looks like 2, 0. And this one looks like 0, 1. Okay. So you said -1, 0. You said 2, 0. And you said 0, 1. So there are our intercepts. Part B wants the domain, and it also wants the range. So let's go back and take a look. Let me erase my little scribbles so we can see better. So the domain, what's that refer to? Yeah, those are your x's. When you're graphing, those are your x's. And it looks like my graph starts at this point here, which is the point -3, good, 2. And it looks like the graph ends at this point, which is good, 3, 2. So remember, domain of the x's. So it looks like it starts at x being -3 and ending at x being a +3. These were solid dots at the end, weren't they? And you feel like, I'm not sure, you're scribbled. Well, let me erase my scribble. These are solid dots. So what are we going to put around the -3 and the +3? Excellent. Brackets. Okay, let's look at the range. The range, we come in from the bottom, because we always read from the smallest to the largest. So it looks like this graph bottoms out right here. And we already decided this was the point -1, 0, and this was the point 2, 0. So regardless of which point it we look at, the y starts at 0, doesn't it? And these were the top of them. And it looks like y ends at 2, doesn't it? Again, I've got solid dots. So what are we going to put? Good. Brackets. Okay, now again, it's asking for where this graph might be increasing, decreasing, and constant. Okay, so let me get rid of a couple of these little scribbles. All right, so we start, or when we answer increasing and decreasing and constant, which variable are we actually answering? Yeah, we're answering with respect to x, so always remember that. So it looks like this graph starts at -3 and decreases to -1, doesn't it? Okay, so we got a decrease start, and we are putting brackets because the author of this book wants brackets. And then when it hits -1, looks like it starts an increase until this point. What is that point? Yep, that point is 0, 1. So it looks like it has an increase from -1 to 0. Okay, and again, the bracket. And then from this point down to this point, from 0, 1 to 2, 0, it looks like it's a decrease, correct? Okay, remember which variable? Look at your x's. So it looks like it decreases from 0 to 2. And then from 2, 0 to 3, 2. Yeah, it looks like it's an increase. And again, we're looking at x's. Looks like 2 to 3 on or for an increase. And that should cover every part of this particular graph. So it starts on a decrease from -3 to -1, because then at -1 it increases to 0, because then at 0 it decreases to 2, and then at 2 it increases until 3. Was there any constant? Was there any constant on this particular graph? Nope, no constants whatsoever. So we write none. And there was one more question. I believe they wanted to know even, odd, or neither one. That's right. Even, odd, or neither. Okay, so let me remind you, if it's even and we're looking at a graph, even means y-axis symmetry. Odd means origin symmetry. So take a look. Do I have, and let me do some erasing here so it's a little bit cleaner to look at. Do I have any y-axis symmetry? Be careful. You're saying, yeah, I do, because this point and this point mirror each other. And that's true. Those two mirror each other. But the question is, does this point, which was -1, 0, mirror this point, which is 2, 0? Nope, it does not. So, do I have any y-axis symmetry? None. Do I have origin symmetry? Yeah, none. So this one is neither. It's not odd. It's not even, because there's no y-axis and there's no origin symmetry. Good? All right, let's take a look at the next one. It's asking me the same question. So I am going to give myself some working room over here. I want to know the intercepts. I want to know the domain. And I want to know the range. I want to know where it is increasing. I want to know where it's decreasing. And where it is constant. And last but not least, I wanted to know if it's even, odd, or, maybe it doesn't fall into either category. So let's start with the intercepts first, shall we? All right, so any intercepts? Yes, I see them also. I see here it's crossing the x-axis, here across the x-axis, here crosses, well, that one crosses x and y, doesn't it? Okay, so looks like it's -pi 0, 0, 0, and pi 0. Do you agree? All right, so let's write those down. -pi 0, 0, 0, and pi 0. Got it. Domain. Domain is, that's right, domain are your x's. So let me just write this point again. This is -pi 0. This one was pi 0. So based upon your x's, where does this graph start? Good, it starts at -pi 0. And this graph ends at pi 0. So it looks like it's from -pi to pi on our domain. Now, were they solid dots? Good, I heard you. You said yes, they were. So that means brackets, doesn't it? Good, let's look at the range. So it looks like it bottoms out at this point and it tops out at this point. And the range refers to your, good, your y's. So it looks like the y's bottom out at -7 and top out at +7. And yet those were solid dots, so I'm putting another set of brackets in there. How we doing? Are y'all with me? Okay. They want to know where it's increasing and decreasing and constant. So take a look at this graph. It starts at this point, -pi0, and good, it decreases until -pi/2, -7, yes? But again, when you're talking increasing or decreasing or constant, yes, you're talking about x values, which means from -pi to -pi/2, I have a decrease, don't I? And we'll put brackets because the author of this book wants brackets. And then from -pi/2, looks like it increases until +pi/2, doesn't it? Okay. And that's right, brackets. And then at pi/2, looks like it decreases until pi, doesn't it? And what are you going to put around that interval? Good, brackets. So we have +pi/2 until pi, brackets, and a little comma. Was there any constant? Nope, no constant. Okay, last but not least, they want to know if it's odd, even, or maybe it's neither one, right? Okay, so remember, even means y-axis symmetry because we're looking at a graph. Odd means origin symmetry. So go back and look. What do we have? Do we have y-axis symmetry? Do I see pi/2, 7 on this side? Nope. Do I see -pi/2, -7 on this side? Nope. I don't see any y-axis symmetry. So there goes even. How about origin? Yep, I see origin because there's pi/2, 7 and -pi/2, -7. I definitely see origin symmetry. So since I see origin symmetry, I'm going to say that this is an odd function. What do you think? Are you okay with that? Cool. So remember, on a graph, I could ask you oodles of questions. I could even ask you for the local mins and the local maxes, or the absolute min and the absolute max. So be very aware. On graphs, I could give you like 10 questions. Good? Okay, so hang in there. There's one more concept for us to go over.
Okay, so one last concept in this section, average rate of change. Believe it or not, you actually already know this. So let's take a look at the definition. If A and B, with A not equal to B, are in the domain of a function, which we'll call f, then the average rate of change from A to B is defined by. Now, here's the thing. I get a little bit lazy and I don't want to deal with writing average rate of change all the time, and there's no variable to represent average rate of change, so I call it AROC, average rate of change. So AROC is equal to f of A minus f of B over A minus B. Does that look familiar? It does if you understand what f of A and f of B represent. What are those? Yeah, f of A is the y value when you plug in A. F of B is the y value when you plug in B, right? Over A minus B. A minus B, they told us, are in the domain. So A and B actually represent, x values. So if you allow me, I'm going to write this as it's the change of the y's. This little triangle means change. It's actually the word delta, which means change. The change in the y's over the change in the x's. Does this sound familiar? Yeah, it sounds like slope. This is actually talking about slope. But the reason they don't say slope is this. Slope is for a linear equation. Linear means line, doesn't it? Average rate of change isn't talking about a line. Average rate of change is talking about non-linear functions. So for example, maybe I have a function that its graph looks like this. And I'm trying to find the average rate of change for this. Well, how am I supposed to find the average rate of change when there's no linear going on? There's no lines going on. So here's what we do. We create a line. So I am going to take this point and this point. You're like, they're kind of arbitrary. In a way, they're arbitrary, but it depends what the authors have chosen or what the people conducting the experiment are looking at. This point has A as its x value, and we find its y value at f of A, don't we? This point has B as the x and f of B as its y after we plug that in, correct? Now, when we draw the line between the 2 points, we now have something linear that we can find the slope of. We have created this line by choosing the A and the B, plugging them in to find the y values that go with it. And now I can find the average rate of change from this x value to this x value. Cool? By the way, this line that we have just created, just so you have a better idea, this line right here is known as a secant line. Back to geometry days. It's a secant line. A secant line cuts through the graph at the 2 points. It doesn't cut through the middle, so it's not a diameter, like a circle has a diameter and it cuts through the middle of the circle. This isn't it. This is off of the center. Cool? Okay, so hang in there. I am going to get us an example so you understand it just a little. So let's take a look at this example. They're asking me to find a rock for this particular function, and the function is negative x to the third plus 1 from 1 to 3. Now, just so you have an idea of what this looks like, I graph the function over here. This happens to be the graph of the function negative x to the third plus 1. Cool? It's that cubic graph, but since the negative is in front, it got flipped over. So some of you may be familiar with this. Now, let's go back to the definition of a rock. To find a rock, right, to find the average rate of change, it's basically finding slope, isn't it? So I need a couple of x's and a couple of y's, don't I? Okay, so here's the question. When it says from 1 to 3, what do the 1 and the 3 represent? Those represent your x's. This is my first x and this is my second x. Are you with me? So I know my first x is equal to 1. I know my second x is equal to 3. And now I've got to find my y values, right? So check it out. When we plug these in, so f of positive 1, right? Let's do the math, so to speak. Let's take care of our arithmetic. And I ended up with 0. Well, there it is, 1, 0, which is what I have graphed anyway. So this would be 1, 0. The second one at 3, when you plug in positive 3, you get, 3 to the third plus 1. This is negative 27 plus 1. This would be a negative 26, wouldn't it? So I'd have the point 3, negative 26, right? Which is way down here somewhere. So just so you have an idea, here's the point 1, 0. 327 is like way down here. So let me continue this graph line. When I connect these dots, this is a very steep line connecting those 2 points, right? So remember, this would be considered the secant line. And these are the 2 points I'm looking at. So I'm trying to basically find the slope between these 2 points. So let's get a rock going. The a rock definition says the difference of the y's over the difference of the x's. So I have 0 minus that negative 26 over 1 minus 3, which gives me a positive 26 over a negative 2, which tells me a rock is negative 13. It makes sense. So because I have a downhill line, my slope is negative. And that's a pretty steep line, which means it keeps going 13 down and 1 over, if you remember slope. So it's 13 down and 1 to the right if you actually put this little imaginary 1 under it. Correct? Okay, so a rock is no big deal. It's just like slope. Cool? Except it's not dealing with a linear graph. It's dealing with a graph that has some kind of curve to it. Good? Okay, so you have fun with this stuff, and I'll catch you on the